Hey everyone, and welcome to The Explainer. Today we're going to crack a code that, believe it or not, runs our entire world. It's the language that's humming away inside your phone, inside the servers that run the internet, pretty much everything. It's the language of digital logic, and by the end of this, you're going to be speaking it. But let's start with a really basic question. Have you ever just stopped and thought about this? How does a computer, which is really just a bunch of metal and plastic, actually make a choice? It seems impossibly complicated, right? Well, what if I told you the answer is actually surprisingly simple? It's elegant, and it all boils down to one tiny concept. So we're going to build our way up from the absolute ground floor here. And you know what that floor is made of? A super simple idea that every single complex problem in the universe can be broken down into a series of simple statements that are either true or false. Now, the key thing here is how strict this definition is. In the world of digital logic, there is no gray area. There's no maybe, no kinda. A statement, or a proposition if you want to get technical, it has to be one or the other. It can't be both, and it absolutely can't be neither. Just think about it like this, right? The sun is never frozen. Okay, that is definitely 100% true. And the moon fits in my pocket. Well, that is just as definitively false. See? It's these kinds of black and white, no-nonsense assertions that computers are built on. So obviously computers don't get words like true or false. They speak a much simpler language, the language of electricity. Is it on or is it off? So we just represent true with a 1 for on and false with a 0 for off. And that's it. This right here, 1 and 0, that's the entire alphabet for the language of every machine on the planet. Okay, so if 1 and 0 are our letters, how do we start making words and sentences? Well, we use a rulebook. Think of it like a cheat sheet that tells a computer exactly what to do with those ones and zeros in any situation it could possibly face. Let's take a look at how this little rulebook works. This guide is called a truth table. And I know it might sound a little technical, but all it really is a simple chart. It lists every possible combination of inputs on one side and shows the one single correct output on the other. It totally removes any guesswork for the machine. And here it is, the simplest truth table of them all. This is for an operation called NOT. It's so simple. If the input is 0, the output is 1. If the input is 1, the output is 0. That's it. The NOT operator just flips the value. It's basically the logical version of opposite day. So now that we get the idea of a truth table, we can use that same concept to define the fundamental decision makers of the entire digital world. These are the operations that form the absolute bedrock of all computing. Get ready to meet and or. All right, let's start with and. Look at this table. To get a true output, a 1 from an and operation, you need input A and input B to both be 1. See that? Any 0 at all in the inputs means you're going to get a 0 in the output. This is kind of the strict one of the bunch. Now, let's compare that to the OR operator. To get a 1 here, you just need input A or input B to be a 1. It doesn't care if both are 1, it's just happy as long as at least one of them is. The only way you can possibly get a 0 is if both inputs are 0. So you can see, it's way more lenient. Seeing them side by side like this really makes the difference click, right? And is all about everything. All inputs have to be true. OR is all about anything. Any input can be true. And this simple difference, this strictness versus leniency, is what lets computers make incredibly complex decisions. And here's the part where it gets really cool, where this stuff gets real. These truth tables, they aren't just ideas on a page. They are the literal blueprints for tiny little electronic circuits called logic gates. We're talking billions of these physical gates, etched into a piece of silicon. They're the microscopic brains of your computer, and each one perfectly follows the simple rules we just went over. So, we've got our rules laid out in tables, and we know they can be built into physical things called gates. But what if you have a really complicated system with tons of inputs? A table would get huge. We need a way to translate these tables into something more powerful. And that's where math comes in. We need an equation. So there's actually a pretty straightforward method for doing this. It's a simple 3-step recipe. First, you look at your truth table and you only care about the rows when the output is a 1. Ignore everything else. Second, for each of those true rows, you write a little and expression. And finally, you just link all those little expressions together using ORs. Come on, let's give it a try. Okay, so here's a slightly more complex table. We've got 3 inputs this time, A, B, and C, and 1 output, which we'll call S. Now, if we scan down that S column, we can see there are 4 different rows where the output is 1. So, following our recipe, we're going to write one AND term for each of those 4 rows. And here's what we get. Each of those 4 chunks of letters connected by plus signs, which just means OR, corresponds to one of those rows where S was a 1. This big thing is called a Boolean equation, and it perfectly describes the logic from our table. But, wow, it looks pretty long, maybe a little intimidating, right? Okay, now for the fun part. What if we took that big, long equation and just built a circuit directly from it, piece by piece? What would that even look like? Let's see what happens when we turn this math into a physical machine. Well, it would look like this. Yeah, it's kind of a mess. Each one of those terms in the equation needs its own little group of gates, and then you have to funnel them all together at the end. I mean, it's functional. It would totally work. But it just feels so complex. It's not very efficient. And that brings us to maybe the most important question in all of engineering. Is there a better way? Is there a simpler way? Could this tangled up web of logic actually be hiding a much, much simpler truth inside of it? Yes. Yes, it can. And this, my friends, is the magic. Using the mathematical rules of something called Boolean algebra, the very same system that gave us that big equation, we can simplify it. And that entire long, complicated expression, it boils down to just this. S equals C. That's it. This right here is the power of what we just did. That complicated, messy circuit on the left does the exact same thing as that single wire on the right. All that extra complexity, all those gates, they were completely unnecessary. The logic told us that the output, S, will always just be whatever the input, C, is. That is the incredible power of simplification. So, the next time you tap your phone screen or click your mouse or do anything with a computer, just remember what's happening under the hood. It's not magic, it's just logic. Trillions upon trillions of tiny switches, all following these incredibly simple true/false rules, all simplified down to their most elegant and efficient form, all working together to create the complex digital world we live in every day. Kind of makes you think, doesn't it?